Section 7.4, Optimization using Quadratic Forms. We'll start with the constrained extremum theorem, where if A is a symmetric n-by-n matrix whose eigenvalues in order of decreasing size are lambda 1, lambda 2, and so on, then the quadratic form xtax attains a maximum value and a minimum value on the set of vectors for which the length of x is equal to 1. The maximum value attained in part A occurs at a vector corresponding to the eigenvalue lambda 1, and the minimum attained in part A occurs at a vector corresponding to the eigenvalue lambda n. So that means that the biggest eigenvalue corresponds to the maximum. When we look at the eigenvector that corresponds to it and we normalize it, then that'll correspond to the maximum. And when we look at the smallest eigenvalue in the corresponding eigenvector, that'll correspond to the minimum. So let's do an example where we find the maximum and minimum values of the quadratic form given over here, subject to the constraint x squared plus y squared equals 1. So that's this thing over here, the length of x being equal to 1, that's basically our constraint. So what we'll start with is writing out z equals 5x squared plus 5y squared plus 4xy in xtax form. So as matrices, that's x, y, maybe I'll give it a little more space, times, let's see, 5 for the diagonal terms, and then 2xy and 2yx for the cross product terms. Then I'll multiply that by xy. Finding the eigenvalues, we'll take lambda I minus a, so that's lambda minus 5 along the diagonal, and then minus 2. That determinant is lambda squared minus 10 lambda plus 21, and that's equal to, when we factor it, lambda minus 7 times lambda minus 3. So we'll set that equal to 0, and we will get eigenvalues of lambda equals 7 and 3. So let's look at the eigenvector for lambda equals 7 first. Since that eigenvalue is bigger, that should correspond to our maximum. So we'll look at 7 plugged in to lambda I minus a, so 7 plugged in over here. So that's 2 minus 2 minus 2, 2. We'll add a column of zeros, and we will reduce this to reduced row echelon form. So notice the second row cancels, becomes all zeros, and the first one we can divide to get 1 minus 1, 0. So that gives us the equation x1 minus x2 equals 0. So we get an eigenvector x. Well, I mean, we get x equals tt just based on that, filling in x1, x2, which gives us an eigenvector where we can factor out t to get 1, 1. And then we can normalize that eigenvector, divide it by its length to get a vector p1 equal to e1 divided by its length. So that would be 1 over square root of 2, 1 over square root of 2. So that is our constrained maximum. So let's look at the minimum now for lambda equals 3. So I'll plug in 3, I get minus 2, minus 2, minus 2, minus 2, and I'll add a column of zeros. And then clearly the bottom row cancels out, the top row I can divide, just get 1, 1, 0. So I get x1 plus x2 equals 0 from the top row. So I get x is equal to minus t by setting x2 equal to t, and then I'll factor out t and get a second eigenvector, minus 1, 1, which I can normalize to get u2 divided by the length of u2, and that will be minus 1 over rad 2, 1 over rad 2. So in summation, we have a constrained maximum z equals 7 for the eigenvalue lambda equals 7 at xy equal to 1 over square root of 2, 1 over square root of 2 from P1. And because that was our biggest eigenvalue, so now our constrained minimum will be at the smallest eigenvalue, z equals 3, or it will be, the minimum is z equals 3, and it will be at the eigenvector given by minus 1 over square root of 2, 1 over square root of 2. These are not the only possible eigenvectors that give us these maximums and minimums. We could have also seen that xy equal to minus 1 over root 2 minus 1 over root 2 and xy equal to 1 over root 2 minus 1 over root 2 would work. Remember that all values of t produce eigenvectors that work here. So we could have factored out minus t, would have gotten minus 1 minus 1. Similarly over here would have gotten 1 minus 1. So we would have just gotten the negative versions. So if you were to put negatives over here, it would still give you the max equals 7. And if you were to put negative here, positive here, it would still give you the minimum. A rectangle is to be inscribed in the ellipse 4x squared plus 9y squared equals 36, as shown in the figure. Let's use eigenvalue methods to find non-negative values of x and y that produce the inscribed rectangle with maximum area. So first, let's write z equal to 4xy. That's the area we want to maximize, since if this is x and this is x, then the length is 2x, and then if this height is 2y, then 2y times 2x is 4xy. So we want to maximize that area, and that's going to be subject to the constraint that we're given with 4x squared plus 9y squared equals 36. Let's rewrite that a little bit to get a better idea of the regular structure for our ellipse. So that would be x over 3 squared plus y over 2 squared equals 1 if we just divide by 36 and then take the exponent out. So how about we take x and set it equal to 3x1, and we'll take y equal to 2y1. That'll help us get the constraint that we want, where x1 squared plus y1 squared would equal 1 under those new variables x1 and y1. So plugging those back into z, we can see that our problem where we have z equal 4xy is maximizing that is the same as maximizing 24 times x1 y1 subject to the constraint x1 squared plus y1 squared equals 1. So now that we have our constraint to equal 1, we can maximize this thing the way that we did it before using eigenvalue methods, and that will in turn maximize the original 4xy. So to that end, let's look at z equals x transpose ax in matrix form. So that would be x1 y1 times, we don't have any square terms, that's great, and we have 24, which splits into 12 and 12, and that multiplies by x1 y1. So let's look at the determinant of lambda I minus a to find the eigenvalues. So it'll be lambda minus 0, minus 12, minus 12. And that determinant is lambda squared minus 144. which factors as lambda minus 12, lambda plus 12. So we get eigenvalues lambda equals 12 and minus 12. Let's look at lambda equals 12 first. So when we plug in 12 for lambda, we get 12 minus 12 minus 12, 12, and we'll append a column of zeros and reduce that. So the second row reduces to 0. The first one divided by 12, we get 1 minus 1, 0, which gives us a top equation of x1 minus x2 equals 0. Maybe I shouldn't have used x2 over here, or x1 over here, because I used it over here, and these are different, but I don't know, I'm trying to be a little consistent with the notation I used before. Maybe you can imagine this is a different letter. Anywho, in any case, we get that our vector x is equal to tt, because we just set t equal to x2 and then x1 equals x2. So then we factor out t, we get that our eigenvector u1 is 1, 1. And normalizing that gives us p1, which is u1 over the length of u1. And that's 1 over rad 2, 1 over rad 2. Okay, so that gives us our maximum area. The maximum area is at our biggest eigenvalue, so that's z equals 12, and it happens when we have x equal to 3x1, which is equal to 3 over the square root of 2, because 1 over square root of 2 is x1, but we have to multiply it by 3 to get the original x, back to where we started. And similarly for y, that was 2 times y1, so that would be 2 over rad 2. The curves in the xy plane, for which the function f of xy is constant, have equations of the form f of xy equals k, and are called the level curves of f. So in the figure, these lines over here that correspond to slices of the function, those are level curves. Geometrically, let's interpret the level curves of the quadratic form given over here, subject to the constraint x squared plus y squared equals 1. Okay, so let's see. We have when this thing is constant, so it looks like it should be constant at 7, as we saw previously, right? Because if we go back up, that's this guy right over here. We saw that it's constant at 7 and 3, right? We set it equal to k over there. So that's subject to the constraint x squared plus y squared equals 1. We calculated those. So how about we write that 5x squared plus 5y squared plus 4xy equals 7 should just touch the unit circle at 1 over rad 2, 1 over rad 2, as we calculated. But remember, the minus ones would also work. So also, we could say it would also touch at minus 1 over rad 2 minus 1 over rad 2. So it looks something like this. Let's see if I can draw it. We have our unit circle, sort of, and we want it to, the level curve could be like this curve that just touches at 2 points. So I didn't draw it very well because the circle looks like it's touching over here, but it's not. It's only touching over here and only touching over here. Okay, so then how about 5x squared plus 5y squared plus 4xy equals 3? Well, that should similarly just touch the unit circle at, as we calculated, minus 1 over rad 2, 1 over rad 2, and at 1 over rad 2 minus 1 over rad 2. So this bigger curve was for the maximum, so the minimum one was going to be smaller. These points were minus 1 over rad 2, minus 1 over rad 2, and 1 over rad 2, 1 over rad 2. So minus 1 over rad 2, positive 1 over rad 2 would be like over here, and the other one would be over here. It's 1 over rad 2, minus 1 over rad 2. And if I want to just touch it, I should be inside then, right? Now that came out a little better. So that inner curve, this outer one was the level curve for k equals 7, and the inner curve was for k equals 3. If a function f of xy has first-order partial derivatives, then its relative maxima and minima, if any, occur at points where the conditions fx of xy equals 0 and fy xy equals 0, remember these are the partial derivatives, are both true. These are called critical points of f. The specific behavior of f at a critical point x0, y0 is determined by the sign of dxy equal to fxy minus fx0, y0 at the points xy that are close to but different from x0, y0. If d is positive at points xy that are sufficiently close to but different from x0, y0, then f of x0, y0 is less than f of xy at such points, and f is said to have a relative minimum at x0, y0. If d is negative, less than 0 at points that are close by but different from, then the function is bigger, so it's said to have a relative maximum at x0, y0. The function at x0, y0 is bigger than all the surrounding points. So the idea is that if d is bigger, then the function at the x0, y0 is smaller than all of the nearby points, so it must be a minimum there. And if d is negative, if it's smaller, so then the f of that point that we're investigating must be bigger than all the surrounding points, so that means there must be a maximum there. But if d has both positive and negative values inside every circle centered at x0, y0, then there are points that are arbitrarily close to x0, y0 at which f of x0, y0 will be smaller than fxy, but also points in which it would be bigger. So in this case, we say that f has a saddle point at x0, y0. It can be really challenging to see the sign of d, so we have this theorem that we often use in calculus, the second derivative test. Suppose that x0, y0 is a critical point of fxy and that f has continuous second-order partial derivatives in some circular region centered at x0, y0. Then f has a relative minimum at x0, y0 if the second partials for x and times the second partials for y minus the mixed partial squared, and it is positive. So f will have a relative minimum there if this is positive, provided that the second partial is positive. It'll have a maximum there if this is positive, but the second partial is negative. So that's the only difference over here. And it'll have a saddle point if this quantity is negative. If this quantity happens to be exactly equal to 0, then the test is worthless, unfortunately. The matrix that we make out of the partial derivatives is called the Hessian, and that's pretty much what we'll tend to use to do our tests. We'll just look at the determinant of the Hessian, because notice if I take this times this and I subtract off this times this, then that's this quantity over here, because of the equality of mixed partials. F partial xy is the same as f partial yx, so we could just write xy twice, multiply those, get partial xy squared, and setting that determinant equal to 0 is exactly what we want to look at for this quantity. So we'll see if it's equal to 0, negative, or positive, really. So that is pretty much exactly what we use to prove this theorem, that the second derivative test can be rewritten in Hessian form. If x0, y0 is a critical point, then if h is the Hessian, f is a relative minimum. If h is positive definite, relative maximum if h is negative definite, f is a saddle point if h is indefinite, and inconclusive otherwise, because then the determinant would be 0. Okay, let's find the critical points of this function over here and use the eigenvalues of the Hessian at these points to determine which of them, if any, are relative maxima, minima, or saddle points. So first, let's organize ourselves and take some partial derivatives. We'll do fx first. Maybe we'll make the x a little smaller. So that's fx xy, and I'm going to keep everything else constant, right? So I just want to take my derivative with respect to x. So looking over there, 3 times 1/3 cancels. I just have x squared. Then over here, y is constant, so x disappears when I take the derivative. I just get the constant in front. And then over here similarly, so I'll just get the minus 8y, and then derivative of a constant is 0. So then let's take the partial with respect to y. So I won't have any x terms. I'll get 2xy, that exponent will hop out. And then I'll get minus 8x. I'll just take the coefficient because x will be a constant in this case, and then nothing from 3. Now let's get the mixed partial. So fxy. So starting with x and taking this derivative with respect to y, we should just get 2y minus 8, because that's gone. And then this is the same as the partial of y. If you took y first and then x, you could check by Clairaut's theorem. Anywho, let's do the second partial with respect to x, and we'll just get 2x, no y terms, and then second partial with respect to y will just be 2x. So now let's look at the Hessian. So we have h of xy is the matrix built out of all of these partials. So I have fxx, fyy along the diagonals, and then I have the mixed partials otherwise. And by the above calculation, this is equal to 2x, 2y minus 8. Don't know why a dot came over there. 2y minus 8, 2x. It was just coincidence that these two are equal. So now we can find critical points by setting the first partials equal to 0. So let's do that. So fxy is x squared plus y squared minus 8y from over here, and that is going to be set equal to 0, and we just have to look at where our other partial derivative is 0. So that was 2xy minus 8x, and I can factor that as 2x times y minus 4. So setting that equal to 0, I see that x would have to be 0 or y would have to be 4. So how about we first try x equals 0 in the first partial derivative equation. So that gives us y times y minus 8 equals 0, right? Because we could just factor out the y from y squared minus 8y equals 0. And that gives us y equals 0 and y equals 8. Now let's test the y equals 4 in there. If y equals 4, then plugging 4 in over here gives us x minus 4 times x plus 4, because this would just be x squared plus 16 minus 32, so that's minus 16. So just factor that. And I'll set that equal to 0, and then I get x equals 4 and x equals minus 4. So I have a bunch of critical points. I have critical points at 0, 0. X equals 0 gives me y equals 0. And I have critical points at 0, 8, because x equals 0 gives me y equals 8. And I have critical points at 4, 4, because y equals 4, and gives me an x equals 4, but I also have it at minus 4, 4, because minus 4 also works for y equals 4. Okay, so 4 different critical points. Let's look at the Hessian of each one. So let's look at h of 0, 0. So h we computed was this. So plugging in 0, 0, we get 0, minus 8, minus 8, 0. And getting that determinant, let's do it for lambda I minus a. So then it'd be lambda over here along the diagonals. So it'll be lambda squared minus 64 if we took the determinant of lambda I minus a, and then factoring that we get lambda plus 8, lambda minus 8. So we can do the same thing for h of 0, 8. That was 0, 8, 8, 0 when we plug in 0, 8 for h. So doing lambda I minus h, I guess in this case not a, but close enough, we have lambda squared minus 64 when we take the determinant, since lambda, and you put minuses, and that factors as lambda plus 8, lambda minus 8. Next we'll do h of 4, 4. So that's 8, 0, 0, 8. We don't even have to bother with the determinant for that one because it's already diagonal. So the eigenvalues are along the diagonal, they're just 8 and 8. Let's get h of minus 4, 4 to finish. So that when we plug in, we get minus 8, minus 8, 0, 0. And again, on the diagonal, so the eigenvalues would just be minus 8, minus 8. So now we can make a table. We can say that for each critical point, we have a lambda 1 eigenvalue, a lambda 2 eigenvalue, and we have some conclusion. For the critical point 0, 0, we have lambda 1 is 8, lambda 2 is minus 8, so we have a saddle point. For the critical point 0, 8, we also have eigenvalues of 8 and minus 8, so again, we have a saddle point. At 4, 4, our eigenvalues are 8 and 8, and notice the other ones are going to be minus 8, minus 8, so this is a relative minimum. And at minus 4, 4, we have eigenvalues of minus 8, minus 8. So that's where our relative maximum will be.